if you have a leaving group, could be a halogen, could be an OH, and you have something that's a lone pair, there's two possibilities. That's why it gets so messy. This lone pair can attack this carbon, and this leaving group will leave. Or the leaving group can leave, then it can attack the carbon. If the compound has, the substance has a lone pair attacks the carbon, it kicks out the leaving group, either by the SN1 or the SN2 mechanism. Okay. In the SN1, this comes, this leaves first, then you get attacked. The SN2, this attacks and this leaves at the same time. But the point is, the atom has a lone pair. If it attacks the carbon, they call it a nucleophile. Okay. Now, if you have something that has a lone pair, and you get substitution, okay. But if you have something that has a lone pair, it can also attack a hydrogen next to it. And then this can swing in here, this can leave. Okay. It can happen all at once, like I do it here, or it can, this can first leave, this leaves, get a positive charge here, then the substance with the lone pair attacks this hydrogen, this leaves. And so it's the same substance, it just, if it attacks a hydrogen, they call it a base. Okay, so bases and nucleophiles are pretty much the same, just a matter of this substance has a lone pair. Does it attack a carbon or a hydrogen? If it attacks a carbon, it's going to be a substitution reaction, and they call it a nucleophile. And that's what we just finished talking about. In this chapter, the substance with the lone pair is going to attack a hydrogen and act as a base, so they call it a base. So these two reactions always compete with each other. Anytime you have something like this, you can get elimination by E1 or E2 mechanism, or you can get substitution by SN1 or SN2. So that's why it's kind of crazy. And in many cases, I'll tell you what reaction is taking place. There's certain tricks you can do to favor one process over the other. Okay? So elimination and substitution always compete with each other. There's only one case where they don't compete, where you can't have elimination, you can only have substitution. And here's the case. If you have a leaving group that's attached to a single carbon, and the rest of these are just hydrogens, well, you can't get a carbon-carbon double bond if your starting material has only got one carbon. So this can only undergo a substitution reaction. If I add something that's a lone pair, it's going to act as a nucleophile. There's no other carbon next to it. But when you start having two carbons and a leaving group, then the possibility exists that you can have, besides substitution, you can have elimination. And you always get a mixture of both products. Okay? Now, remember how you learned the SN1 and SN2 mechanism? You have to give me the E1 and E2 mechanism in the next test. Okay? And as the name suggests, the E1, only one substance is involved in the slow step for E1 mechanism, and for E2 mechanism, two things are involved in the slow step. So let's do the easier one of the two. Let's do the E2 mechanism. If I give you the starting material, so here's the next test question. If I give you something like this, and let's make the leaving group a halogen. And remember, if the leaving group is a halogen, you don't need to do anything special in advance. It's going to leave, it can leave as a X minus. Okay? If the leaving group is OH, then you're in trouble. Then you got to do something this to make it better leaving group. Okay, so let's start off with just a halogen, that makes life easier. And I'm going to add something that's a lone pair, and it's going to attack a hydrogen, so I'm going to call it a base. Okay? And usually it's negatively charged. And you just close this swings down here, and this leaves. And you get your products. So I'm going to give you the starting material, this guy's here, and the products. And I'll ask you how to, and I'll tell you this is the E2 mechanism operating, and I'll ask you to show me the arrows. So I didn't draw very nicely. But anyway, so just imagine seeing this without the arrows, and you see in this, so how do I go from here to here by each mechanism? So I'll be looking for 3 arrows, and it will be a single step, just one step. And this single step involves 2 things. It involves the substrate and the base. See, so the rate of this reaction depends on some rate constant K times the concentration of the substrate, which is Lg leaving group, times the base. And typically, not always, but typically, if the base is a strong base, it's not going to hang around and wait for this to leave. It's going to attack this hydrogen, and this will then force this to leave. And once this hydrogen gets pulled off, these purple electrons swing down here, and it pushes these electrons out of the way. All right, so what you learn about SN2 mechanism, strong bases favor it. Same thing here. Kinetics, second order kinetics. This, if you double the concentration of this or this, the rate doubles. Okay. All right, so that's pretty easy. And just like before, the SN1 mechanism is a bit messier, while the E1 mechanism is a bit messier. We get a carbon cation. So this could also go by another mechanism, especially if I have a weak base, like.
Did you say strong bases favor SN1 or SN2?
E2 and SN2 and E2.
Okay.
Who knows? Who knows what I said? I'm always saying the wrong things, so I may have get it wrong. But let's remember, yeah, strong bases, which typically, not always, but typically are negatively charged. They tend to favor the SN2 mechanism and the E2 mechanism. And then weak bases, which typically, but not always, weak bases tend to be neutral. They tend to react via an SN1 mechanism or E1 mechanism. So here's a weak neutral base. I can find one my bag of tricks. Let's just take water. See, this top one could have been hydroxide ion. See? So the hydroxide ion could pull off, that could be my base, that could pull off a hydrogen, this is what you did. Now water is not going to be basic enough to pull off this hydrogen. This hydrogen is not acidic enough to be pulled off by a neutral water molecule. So instead, first step in the mechanism, by the way, this is the starting material, and here is the product. Okay, so there, everything you see, now I'll tell you this goes by the E1 mechanism. Here's what I'm looking for. I'm looking for the first step, this. This is going to be the slow step. You're going to form the carbocation. So it's just like before, no difference before. Okay? And this is the slow step, so the rate of this reaction, because this is the slow step, only depends on what's involved in the slow step here. See, so we say it's first order kinetics. The rate depends on the concentration of the substrate. Because in the slow step, you don't have the base involved. All right, so now this is formed. So now the second step, oops, now this attacks this. This hydrogen now is more acidic. It doesn't mind being attacked. It's got a plus charge nearby. In other words, this plus charge kind of pulls with these electrons, makes this more susceptible to attack. So these electrons are pulled down. This weak base can attack that, and this pair of electrons swings in. Okay. Now the nice thing about this is you are done. You get your product. Okay. Now, what you do have, which I don't care about, you have this, and you have Br minus. Okay? And then the Br minus attacks this, and you get water, or HBr and HBr. But remember, we don't give a hoot about the other products. See? So you don't need to show me this step here. We don't care about this. So this way, you can get away with basically 2 steps. First step, formation of the carbocation. This bond breaks, you form this. Second step, this weak base now can come in and pull off this hydrogen, and this electron swings in each product. See, so I'm looking for 2 steps, and 1 arrow in the first step, and 2 arrows in the second step. So So it's a little, not as messy as the SN one mechanism. And I'll tell you, that this reaction, once you form this carbocation, this could also attract the carbocation. You get substitution, you get an OH, see? So how do you know, chemists have little ways to favor one over the other, but you're not gonna know at this stage. So I'm gonna tell you, I'm looking for the elimination product or the substitution product, okay? And since we're doing preparation of alkenes, I'm going to do the elimination product. So those are the two mechanisms you want to make sure you know. And I'll probably use an alkyl halide because it's a little bit, it's tidier if I use an alkyl halide. Okay. But these reactions, halogens can leave, they don't need that much help, but OH can't leave. OH is a bad neighbor. So instead of having an halogen here, like bromine, chlorine, fluorine, iodine, you have an OH, you got to work extra at it. And you did this in the lab, those of you who take the lab, and some people do it, well, no, we've already did that. You did a dehydration. By the way, this is called dehydrohalogenation because you're taking away a hydrogen and a halogen to make the alkene. So they refer to this as dehydrohalogenation. Now, what about this reaction? You want to make sure, I'm probably not going to ask you for the mechanism, but I definitely want to ask you for this reaction. Probably one of the most common reactions you will get in chemistry. And if you take a standardized test, a PCAT or MCATs or DentalCATs, they're going to have this on the test. It's always, commonly done. And we did it in the lab. Okay? Alkenes are very, very important compounds, and alcohols are very common compounds. You can take an alcohol and make an alkene. So how do you go from this picture to this picture? You add sulfuric acid and you heat it. Now in the lab we use sulfuric acid and also phosphoric acid, those you take the lab. We start with methyl hexanol. I think we went 2-methyl cyclohexanol, and we made a cyclohexene, methyl cyclohexene. But anyway, this is not going to leave. See, so what you have to do first, you got to protonate. Now, don't worry about this mechanism. This is going to kind of show you what happens. Now, this is a good leaving point. So, this pair of electrons can be taken, this bond will break, and you use water, and you get this. Okay? Now, you do this reaction, usually you have sulfuric acid or phosphoric acid in water, and so the next step is just a water molecule. Just takes away this hydrogen, just flips it here, and you get your product. Okay? So it's basically an SN1 type mechanism, this dehydration reaction. Goes by, E1 mechanism. It's just an extra step. You got to protonate this first. Now this can leave, and then after it leaves, the base, it won't be a negatively charged base because you have an acid. See, if you have an acid, you're not going to have a negatively charged base. They react with each other. So you did this in the lab, though you take the lab, you added phosphoric or sulfuric acid, it was in the water, you heated it, you protonated this is left. You got this, then the water spoils this off and you get your final product. Don't worry about the mechanism. Just give me the product of this reaction. Okay? And in this next test, I'll probably ask you for the starting materials. I'll give you some examples in a minute. So those are the mechanisms you want to learn. E1, E2, but with the halogens, not with the OH. But it's simple. Now, we talked about this last week. Let me just refresh your memory. There's no restrictions whatsoever on the stereochemistry. If the E1 mechanism is operating, it doesn't matter which directions in space these guys are pointing. It's going to eliminate, okay? It doesn't matter. So, if you have this,